Continuing on our discussion of periodic trends, we want to talk about ionization energy and electron affinity. So ionization energy measures the amount of energy required to create a cation. So what we're now looking at now is not just static properties of atoms, but this is going to be a tendency for atoms to react. What we're going to start to look at now is periodic trends that are explicitly looking at the reactivity of atoms. Ionization energy, if you have, say, an atom and you're removing an electron to form a cation, that is always an endothermic process. You always have to put in energy. We can see that the energy is like a reactant. And so if you have really large ionization energies, that means it takes a lot of energy to remove an electron from the neutral atom. So that's a stable atom. Low ionization energies imply it's relatively easy. They're always going to be positive, but for atoms with low ionization energies, it's really not that hard to get that electron to come off of it, off the atom, and form an ion. And forming an ion is a chemical change, right? These are starting to be chemical processes where we're going to start to see, this is where we're going to start to look at reactivity and how we can see, we'll see that the periodic table will inform patterns of reactivity. All right, so if we want to look at our periodic table, kind of our little map of the periodic table, the trends are such that as you go across a period from left to right, we increase in the ionization energy. So this increase implies that those electrons are more tightly bound, and that actually we can understand it in the same way that we talked about size. Right, as we go across, there are more protons, right? Higher atomic number, more protons means that those electrons are experiencing more positive charge. They want to stay on the atom because there's plenty of positive charge to go around, and they're more tightly bound. So for the same reason why the atom is smaller as we go across the period, the ionization energy is higher. For groups, going down a group, the size gets larger. Those electrons are further and further away from the nucleus, and as a result, they're going to be bound more weakly. It is easier to take an electron off of something when it's further away from the nucleus. So as a result, atoms get bigger as we go down, so the ionization energy increases as we go up. Those electrons are closer to the nucleus. They are more tightly bound. So overall, we have our same endpoints. The atom with the largest ionization energy is helium, and the energy with the smallest is francium. And this is the opposite of size. So ionization energy trends are just the opposite of the size trends. Helium is the smallest atom. Those electrons are closest to the nucleus. As a result, helium has the largest ionization energy. Francium is the largest atom. Those electrons are the furthest from their nucleus. It's the smallest ionization energy. It is the easiest to remove. It is very hard to form helium plus. It is relatively easy to form francium plus. And if we look, this kind of makes sense. Our whole idea, everything on this side, the noble gases have the highest ionization energies of their period because they really don't want to form cations. They don't want to form ions, period. They definitely don't want to form cations. Over on this side, the other side, on the alkali metals, have the lowest ionization energies for a given period because they tend to want to form those positive cations. So removing that single electron, yes, there is always a cost. They don't just spontaneously or naturally lose electrons, but it's not that hard to remove the electron. They are weakly bound. They tend to form cations. With that in mind, we want to take a look at working through some examples of arranging our atoms by ionization energy. And so we got bromine, calcium, gallium, and germanium. And again, when we're looking at periodic trends, the first question is always going to be, how are these atoms related on the periodic table? So bromine, calcium, gallium, germanium, where are they on the periodic table? What does that look like? And then what's the trend for that direction of the periodic table? All right, so if I take it, I got Br, Ca, Ga, and Ge. I want to find where they are on the periodic table. Highlight them all right there. I can see they are all in the same period, right? They're all in the same group. And I know that ionization energy increases across a period from left to right. So I know the increase is in this direction. So if I want to say the question was in decreasing, I know that whatever's closest to the noble gases is going to have the highest ionization energy. So bromine, then germanium, then gallium, then calcium. And I can be confident that, this makes sense, right? We would expect that bromine, because underlying, we know that bromine tends to form anions. It really doesn't want to form cations. That's not getting closer to stability, and so that is really going to have a high cost to remove those electrons. Whereas calcium, we know in the end, this calcium is going to lose 2 electrons. So there is still going to be a cost. It's always endothermic to remove an electron, but getting off 1 is going to have a lower cost than it would for gallium or germanium or bromine. Okay, so we can look at a little more in depth on ionization energy. One of the things is what we've looked at so far is actually called the first ionization energy. And the first ionization energy is the energy required to remove a single electron from an atom. We've always looked at just taking 1 electron off. We could do beyond that, though. We could have a second ionization energy. We could have a third ionization energy. So the second ionization energy is the cost to remove the second electron. And ionization energies always happen one at a time. You always remove a single electron, making your way up, forming a higher, slightly higher and higher charged cation. And you can define as high as you want. You can see for lithium, it's limited to only a third ionization energy. That comes from the fact that lithium only has 3 electrons, right? So you can't have a 4th one because there's no more electrons. Beryllium similarly is limited to only being the 4th for similar reasons. Calcium at atomic number 20 could have 20 ionization energies. You're removing those 20 electrons one at a time. And if we look at these ionization energies, we can, kind of think about, well, what would that kind of be? We can see that one of the things is as we go across a row here, so for a given element, as we remove more and more electrons, the cost gets higher and higher. We will note they are always positive because removing electrons is always endothermic. It doesn't matter if it's the first, second, or third, but it becomes more endothermic. And the reason for that fact is that you're removing an electron from something that's already positively charged. You have something that already has more electrons. One of the things we also said is that cations are smaller. We know that for this generic atom, that when it becomes a cation, it is smaller. Those electrons are closer to the nucleus. There will be more of an energetic cost to remove that next few electrons. It's always going to be smaller, and it's always going to therefore be harder. You can also think about you're taking something negative away from something that's positive, and that's going to be more difficult to do. Like charges are attracted, so the electron is attracted to the cation overall, and you have to pull it away. The higher that charge is, the smaller the cation is, the more tightly bound that electron is, and the more you have to pull away from to overcome to remove that electron. So it doesn't matter what row you look at, the numbers always go up. Subsequent ionization energies are always higher. But they are not always increasing in the same magnitude. For example, if we look at sodium, okay, so that is 496 for its first ionization energy, magnesium is 738. And so, it makes sense that it takes more energy to remove an electron off magnesium, that is to the right of sodium on the periodic table. But if we look at the second ionization energies, they both go up. Sodium goes from 496 to 4560, whereas magnesium goes from 738 to 1450. So they both go up, but we can see that sodium has a much larger jump, right? It's like 10 times higher, whereas magnesium is only about 2 times higher. And so there's different magnitudes, and if we look at any given pair of atoms, there's always going to be a difference in that magnitude of jump that we see. Sodium's is a lot higher to go from the first ionization to the second ionization. So in order to learn these jumps and what's going on, let's take a look at what sort of electron configurations these atoms and ions have. So first ionization energy corresponds to taking an electron off of the neutral atom. So let's look at what we would be taking it off of. Sodium is 3s1 as its valence, and magnesium is 3s2. We know when we're going to form a cation, we're taking that highest energy electron, so it's going to be from that same 3s state. Magnesium is a little bit of a higher energy. We can see it's 496 versus 738. It's a little bit higher energy to take it off of that magnesium because the magnesium has more protons, it's a little bit smaller of an atom, a little more tightly bound electrons. So we can take it off, but they're still on the same order of magnitude. If we go to look at the second ionization energy, though, we can see that magnesium goes up as we would expect. Sodium goes up as we would expect, but by a lot. It is almost 10 times more energy to take that second electron. For that second ionization, to see what we're taking an electron off of, we now need to look at the singly charged cations. So for magnesium, taking out that second electron still implies removing an electron from the 3s orbital, right? For magnesium atoms, it was 2 electrons. We took 1 out of the 3s. For the magnesium plus cation, there's taking 1 electron out of the 3s orbitals. And then we can see that, so overall, it's going to be the same type of process. Yes, we're taking off an electron off of a positive cation. Now it's a little bit smaller, so it's a little bit higher, but you're taking electrons out of the same type of orbital. When it comes to taking an electron, the second ionization of sodium, with the sodium plus cation, now your highest energy electron is in a 2p state. And actually, if we look at this sodium plus, this is a noble gas configuration. This is isoelectronic with neon. It has 2 electrons in the 2s and 6 electrons in the 2p. This would be a very stable state. This is, the type of desire. This is where sodium wants to get when it forms an ion. So taking another electron out of this state is going to have a much higher cost because now you're taking it out of a lower state. It's a 2p subshell instead of a 3s. And it's a particularly stable subshell for the reasons of, you have everything nice and full and you'd have to break that. So this second ionization energy for sodium plus is going to be the same as the ionization energy of neon, but even a little bit higher because it's more tightly bound. And we can understand if we look then at the third ionization, it's not when we see now, okay, well, let's keep going, let's keep taking more atoms. We can see in this case that, hey, magnesium in this one has a huge jump, right? It goes almost, 7,730. Sodium has a less large jump, but it's still really high. Because in this case, when now we're comparing, if we're taking the third ionization, we're taking electrons out of the 2 plus cation, and we can see it's a more apples to apples comparison. We're taking electrons out of 2p states on both of them. Magnesium just has the big jump between second and third because that's where the difference occurs between are you taking it out of the 3s or out of the 2p. For the sodium, that jump happens between the first and the second ionization. So, those first, really the question is when we see it's always going to go up and it's going to jump up a lot when we hit that noble gas-like configuration. So for sodium, that's at 1. For magnesium, that's at 2. For aluminum, that's at 3. So one of the things we can start to see here is these periodic trends and these patterns in ionization energy are actually the roots of where we see what things tend to form cations. So all of that explanation of this idea that, the alkali metals form +1, alkaline earth metals form +2 is really all based on these ionization energies. Sodium doesn't think, it doesn't say, oh, I only want to get 1 or lose 1. It just so happens that the barrier to lose 1 isn't that high. It can get that energy from other places, but there's not many chemical processes that are going to give you 4,000 kilojoules per mole that allow it to drive that endothermic process of removing that second electron. So, it can lose electrons, but it can't lose more than that first one because that's just a really high cost. When we say that these are more stable as noble gas, it's not that these atoms think that. Just functionally, since they are more stable, those electrons aren't going to leave the atom. There's just too high of a penalty for an atom to lose those sorts of electrons. All right, so we formed cations. Well, now we want to form some anions. And so this would be defined by electron affinity. And electron affinity is the energy change associated with the addition of electrons, right? That's forming anions when electrons join atoms. And it's going to correspond to the value of delta H. So this is usually an exothermic process, but the electron affinity tables generally show positive values. So we're forming anions. Forming anions is usually exothermic. And so, for example, fluorine. Fluorine has an atom plus an electron to make fluoride has a delta H of -328 kilojoules, so very exothermic. However, if you were to look up the electron affinity of fluorine, it would be given as 328 kilojoules. The motivation for this is you turn it positive as basically an idea of how much energy this fluorine atom would be willing to, quote, spend, right? It would be giving away this energy, and so it could go into something else. And so that's why you write it as a positive to go into there. The other reason why we turn it positive can be understood if we look at the trend. So we go to our periodic table. For electron affinity across a period, the increase in the number of protons causes electrons to be more tightly bound. Atoms are smaller, so the electron affinity increases. What that means is it would be more exothermic for an atom to gain an electron, so that we get an overall positive value, higher positive value. Going down a group, valence electrons are further from the nucleus, they are bound more weakly, and as a result, there is less bang for your buck. You don't have a high electron affinity because those electrons aren't going to be that tightly bound. The smallest electron affinity is francium. The largest electron affinity is fluorine. It's a little bit different. It's not going to be helium like we've normally seen because noble gases don't form ions. So overall, though, fluorine really wants to become fluoride. Fluoride is very much an exothermic process to form that fluoride, and francium really doesn't want to become Fr-, right? Because it wants to become Fr+. We know that. And overall, if we look at this slide, this is the exact same explanation as ionization energy. This is why we flopped the sign where we make electron affinity just positive, so that way it matches up with ionization energy, so that way the increase is in the same way from left to right on a period and bottom to top on a group. Just so that way they're the same, so you just have to, remember it's the same increase. You just then have to know that electron affinities do get swapped. That's going to do it for chapter 6. So we started way back talking about light as a wave, light as a particle, moving through quantum mechanics, and then a lot about electrons around atoms. And so we got all of our nice kind of ideas, ending here with periodic trends. I encourage you to take a look at the labs this week for this module. They're going to be dealing with these chapter 6. First off, emission spectroscopy to looks at light and how that's related to the quantization of electrons. And then the periodic trends explores these last concepts. So it's kind of the labs cover the very first and the very last concepts from chapter 6.